all over the world. I would like to request Dr.
Initially, I would like to thank the organizer for inviting me and allowing me to present my research here. Honorable Chair, Co-Chair, and my respected teachers and their audience. This presentation is a part of my Master of Philosophy thesis, which has been carried out at Department of Chemistry, BUET. And this study was very important to me because this degree helped me to achieve highly competitive PhD scholarship in Australia. Now, I would like to talk a brief background of my research. Let us start with the sources of dyes in the environment. Major sources of dyes in the environment include paints and varnishing industries, textile industries, pharmaceutical industries, treated or partially treated effluents, food industries, leather industries, household activities. So these dyes in water body creating a huge problem to our environment. So why dyes removal? Especially textile industries release a huge quantities of wastewater which primarily contains various types of dyes. These are extremely hazardous, toxic and carcinogenic to human health and aquatic lives. And exposure to high levels of these dyes can cause severe health problems including cancer. Now the question is, how can we remove these pollutants from the water body? Well, it's simple using nanotechnology driven nanomaterials. So nanomaterials, as my previous speaker already says about this, iron nanomaterials. Nanomaterials have received increasing interest owing to their fundamental properties, and most importantly, nanomaterials have large specific surface area, low to moderate surface charge, mesoporous structures, which enable them to absorb various types of pollutants from water body. And they also have applications in various fields, including electrochemistry field, catalysis, sensor, supercapacitors, etc. So our approach is to use metal oxide based nanomaterials in wastewater treatment. So we use zero valent iron nanomaterials, metal oxide nanomaterials, mixed oxide nanomaterials, and bimetallic nanomaterials to absorb various types of pollutants, primarily organic dyes. So here I have shown various types of nanomaterials, iron-based nanomaterials, manganese-based nanomaterials, aluminium-based nanomaterials, and other nanomaterials. Our target is to use manganese oxide-based nanomaterials because these manganese oxides are available in soil, sediment, and aquatic environments, and these are very simple to prepare in the laboratory, and they are environmentally friendly. And we use adsorption. There are numerous technologies for the treatment of wastewater. For example, coagulation, flocculation, adsorption, reverse osmosis, microfiltration, nanofiltration. Our approach to use adsorption because it's very simple and we can use it very easily, and most importantly, it does not produce any secondary sludge. So we use adsorption, and then we synthesize manganese dioxide nanoparticles using the reduction of potassium permanganate by manganese sulfate, and the whole protocol is shown here. finally I got this manganese dioxide, and here is the reaction for this synthesis. Then I synthesized osmanite from the forced hydrolysis of manganese to acetate, and whole protocol has been shown here. Finally, we got this osmanite, and here is the reaction. Finally, we prepared manganite. Actually, our approach was to synthesize mixed metal oxide nanomatrix. So we used the reagents for the synthesis of manganese dioxide and osmanite combined using similar protocols, and ultimately we got manganite. This was really interesting for us, and then we characterized these substrates using FTIR, XRD, SCM, EDX, dynamic light scattering, EZDTA, point of zero source, specific surface area analysis. So here I have shown the results for FTIR spectra, the corresponding bands for these three substrates well matched with literature available: manganese dioxide, osmanite, and manganite. Then we studied XRD analysis from these three samples, which has been done in Atomic Energy Center. So from this study, we see that for these two cases, there are a lot of noise, which means the particles are weakly crystalline. On the other hand, if we look at below, it is showing that peaks are relatively sharp, which means it is fully crystalline. Later, we also determine crystallite size, I will show you later. And then we also took SCM analysis at different 3 pixels. So from this, we see that particles are rod-like with different sizes. Then we also see SCM of osmanite. So from this, we see that there are different shapes and sizes particles. It's looking like aggregated particles. Then we also study SCM of manganite, and so it is clearly seen that particles are aggregated. And we also studied elemental analysis. So from the composition of manganese and oxygen, we found that these three substrates were manganese dioxide, which is barnesite, osmanite, and manganite. Then we determine point of zero source, which is the most important property for any adsorbent, using simple acid-base titration. Nowadays, we use zeta potential for determination of surface charge. So here I have shown the determination of point of zero source at 3 different concentration of electrolyte sodium chloride solution, and we see that 3 curve intersect at 8.8, this case 8.75, and for this case it is 9.8. This means the point of zero source are this, which means the pH at which the surface, the concentration of positively charged surface and negatively charged surface are equal. That is known as point of zero source, or in short we call it pH is at C. Then we determine another interesting property of adsorbent, which is specific surface area using methylene flow adsorption method. And initially we studied isotherm study for monolayer adsorption capacity determination and then we determine specific surface area using this formula. And so these are the summary of our results for characterization, which indicating that manganese dioxide is tetragonal and weakly crystalline, and osmanite is body centered tetragonal, manganite is monoclinic and crystalline.
5 minutes.
Let us start our removal study. I used an effect of pH, effect of contact time, effect of dye concentration, effect of adsorbent use to understand removal performance. And here is the spectra for methylene blue and orange green. Methylene blue is a cationic dye and orange green is a typical anionic dye, and methylene blue has got lambda max of 664, while in case of orange green it is 477. I have also determined molar extinction coefficient. Then kinetics of methylene flow adsorption. So we see that the spectra of duration of dye with time, and it is interesting to see that the adsorbance increases with increasing contact time. And here is the pictures of before and after adsorption for these two dyes. And to understand the mechanism of dye adsorption, we studied adsorption kinetic models and adsorption isotherm models. Here I have shown the results for C to first order and C to second order model. So from this calculations, we clearly see that regression coefficient for C to second order is much more higher than C to first order, which means that our data potentially describe C to second order model. This implies chemisorption step, and then we studied Langmuir models and determined the parameters, and then we also fitted Freundlich isotherm models, and these are the results. So if we compare the R square value from this and this, we see that the R square value for Langmuir isotherm is lower than R square value of Freundlich isotherms, which means that our data follows Freundlich isotherm models, which means dye adsorbed onto manganite surface by forming monolayer onto heterogeneous surface. Then we also studied effect of pH. It is interesting to see that the percent removal of methylene flow increased with increasing pH. This is primarily for surface property of manganite. And interestingly, the percent removal for orange green initially increased maximum, then decreased again. However, it is also for the surface property of manganite. So from our study and previous literature introduced mechanism of dye adsorption. So dye molecules adsorb onto the surface by electrostatic interaction, van der Waals forces, hydrogen bonding, interparticle diffusion, and most importantly, surface complexation. Surface complexation involves two forms. One is inner star complexation. That means when there is no water molecules between adsorbate and surface, that means there is direct chemical bond formation, which is known as inner star complexation. However, in case of outer star complexation, there must involve a water molecule between adsorbate and surface. So, from this study, the key findings are dye removal efficiency was found to depend on various factors, including nature of substrate and experimental conditions. And dye degradation data follows second order and Freundlich isotope model, and adsorption mechanism primarily involves physics option, hydrogen bonding, chemical option, ion exchange, and precipitation at higher pH. And thinking that manganite was found efficient adsorbent for removal of other dyes. These are the reference. So from this thesis, I have published two review articles in a Journal of Water Process Engineering, whose impact factor is 7.34 G1 and Scopus index, and some others are in manuscript space. So I would like to thank Aminul University Authority for giving me opportunity to do research here in BUET, and I also acknowledge Department of Chemistry BUET for giving me opportunity to do my research. And I am really thankful to my respected teachers who supported me a lot during my completion of MPhil thesis. And I have a YouTube channel. My research activities can be found here. This is Aminulchem, and thank you all for your kind attention. That means methylene blue and orange green was prepared in aqueous solution, but we did not get time to use actual effluents, because actual effluents contain various types of dyes.
Dyeing, they use various kind of things.
Yeah.
So that time it will be more difficult to remove.
Yeah, it's really difficult. Yeah.
Okay, thank you. I have a very simple question. We prepare nanoparticles because of the large surface to volume ratio, large surface area, big surface area. But I see our particles are exudated. This surface area is blocked. So, how we can stable the particles? For this application.
I also studied the stability of my nanoparticles with variation of pH. We found that nanoparticles are stable within the pH range of 4 to 8. Beyond 4, below 4, and beyond 8, particles become dissoluted or whatever is called precipitated. In our case,
But if your particles are stable below 4 pH, but I see you have different absorption efficiency at different pH. What's the chemistry? What's the chemistry here?
Oh, okay. Thank you so much for this interesting question. Actually, we have shown that the point of zero source, for example, point of zero source is 7.5. It means 7.5, the surface is positively charged, which will attract negatively charged pollutants.
Yes.
On the other hand, beyond 7.5, the surface is negatively charged, which will attract positively charged pollutants. Here we have shown for case of methylene group, we found that absorption capacity is higher at higher pH due to surface charge.
That's the question. We have negative, we have particles, we have surface.
Yes.
What we have on the surface that can show positive at below pH, that can show negative at higher pH.
Interesting. It's surface functional group.
With what are the groups?
OH group, it could be OH group or SH group. So in our case, it is OH group.
Particle is coated with some function.
Yes.
Particles are
When
coated with some
nanoparticles are hydrated, we hydrated 24 hours, then particles become positively charged or negatively charged based on pH.
Maybe afterwards we can talk.
There's
Okay,
some
so
coating. There is some coating on the surface.
No.
No, I did not use any coating. Just if you hydrate the surface, if you hydrate the surface or absorption in water, for example 24 hours, it will automatically produce positively charged and negatively charged based on solution pH, as I said before.
But you show if particle is coated with some function to COH, at higher pH it will be ionized. At lower pH it will be no ionized.
No, in our case we directly use manganese oxide nanoparticles, so it was not coated with something else like surfactant. We did not do so.
But if we don't have any surfactant, any polymer, any other small molecules,
How
it's
is
really difficult to change from positive to negative.
Yes.
Just only the way. This is my experience.
okay, so dear audience, I think
Okay.
thank you very much.
It
Actually,
is going to do Professor Dr. Nothing.
Yeah.
This is working. So each your best this one. I probably
Maybe
Yes,
we
sir.
can.
You can talk with him.
Okay, thank you so
Okay,
much.
thank you.